This is it. This is the last quiz in Regents Chemistry, and it's on radioactivity. I have pulled in both Table O and Table N because you're going to actually end up needing both likely for most of these questions. For the first few questions, we are going to be filling in what's missing. And in order to fill in what's missing, you really need to look at Table N. So before we can figure out what's actually missing in that reaction, we need to figure out what mode of decay the substance would undergo. So we're going to look through our nuclides here that are given, and I'm looking for P32, here it is, and it goes through beta minus, beta negative decay. I'm just going to kind of pencil that in over here, because then I have to look in Table O to figure out, well, what particle would it emit as a result of that? So over here under the symbols, here's beta minus, and we have a choice of two different notations here to use. So that I'm going to leave up to you, but you need the 0, you need the -1, and then you can either use the E, because really it's an electron, or the beta in order to fill that in. Now, the top number, or the mass, needs to total the same on both sides of that reaction arrow. Since on the reactant side it totals 32, on the product side we need the same. Since this is 0, it's going to be 32 on top. And then the same thing is true for the bottom number, but in order to figure out what the bottom number would be, you're going to need to look in the periodic table for the atomic number of phosphorus. I happen to have that memorized. It is 15. So my total on the charge, or on the bottom number here, needs to total 15. Since this is -1, the other one's going to have to be one more than that to make that work. And again, in order to figure out what element this is and which symbol then to put next to it, you're going to need your periodic table. I once again have this one memorized, so I don't need to, but it is sulfur. So you just look for atomic number 16 in the periodic table. Next question, we have boron, and it has a mass of 11. And they've actually left the blank on the reactant side, which means that they must be hitting the nucleus of boron with some particle. And then they're getting these two products as a result. So we're going to need the atomic numbers of everything here. And then we'll also look at the masses. This time I'm going to bring in the periodic table. I want to be sure you know where to look for each of those things. So just a reminder, the periodic table is where you're going to find the atomic number of each of the elements and its mass. And it may be tempting to use the mass from the periodic table for these questions, but the mass is actually given to you because the isotopes that we're talking about have specific masses, and you have to use that isotope. Remember that the masses given in the periodic table are actually the weighted averages, or the average isotopic masses of the naturally occurring isotopes on this planet. So for boron, the atomic number is going to be 5. So I'm going to fill that in here. And then helium is one of our noble gases, and it is way over here, and it has an atomic number of 2. So I'll fill that in right here. And then the last one we need to look up right now is beryllium, and its atomic number is 4. So if we look at just the atomic numbers, or the charges, on this side right now it totals 5, but on this side it's totaling 6. So I need to have something that has a charge of 1 in order for the math to work out. And then up here for the mass, on this side right now it totals 11, but on this side 8 and 4 it totals 12. So whatever particle this is, it also has a mass of 1. To figure out the symbol of this particle, I'm going to look in Table O to find something that has both a mass and a charge of 1. And here it is, and we have a choice. This is a proton, and we can either say 11H, because really the symbol of something that has a charge of 1 is going to be hydrogen, because hydrogen has a mass of 1 and a charge of 1. It is really only a proton. Or you could put 1/1p, because like I just said, it is a proton. So whichever way you would rather denote this, I'm going to use H because that's easier to write for me. All right, the next one, we are given Cobalt 60 and a reaction arrow. So we're not bombarding this with anything. It has two products because there's going to be a radioactive particle and there's going to be what it transmutates into. So here is my table N, and right here I find Cobalt 60, and it decays by beta minus. So I'm going to put that away for a second, and I'm going to put this here as a little note while I then pull out table O and beta minus again. I have the choice of one of these notations, whichever you prefer you can use. Oops, that should be a 0, -1, and I'm going to use beta again this time. All right, so now my mass and my charge need to total the same, so I should probably look up Cobalt's atomic number. Here it is. It's number 27. And I'm going to put that over here because that'll remind me that my total charge needs to total 27. Since this is -1, the charge on the other particle, or what element this is going to transmutate into, has to be 1 more than that. Since the beta particle has no mass, then the mass of this new element has to also be 60, like so. And then we'll look up in the periodic table to figure out what atomic number 28 is. And here it is nickel, and that's the symbol that I am going to put in right here. Number 4 asks which of those are natural transmutations. Natural means that they would transmutate, they would undergo a nuclear reaction without any bombardment. So essentially, if what you wrote out as a reaction only has one reactant, it is going to be natural. Or if you find it in table N, it's going to be natural. Those are all naturally radioactive elements. So I'm going to say 1 and 3. And this one we're not asking you to explain it because there's a lot of ways you can guess wrong on that. So I'm going to assume you're not guessing if you got it right. Which of the above represent fission? Fission is when a nucleus splits. Some people would tell you that it has to be specific isotopes that go through fission. I'm going to accept that any that actually split without bombardment are fission. So we're going to accept both 1 and 3. Number 2 is fission in a sense, but it's not a natural fission. It was an artificial fission that had to happen. Number 6, write a decay equation for radium-226. So don't get confused. This says decay equation. That's just a transmutation reaction, just like the ones we did in 1, 2, and 3. But you're going to be writing the whole thing out. So we have radium-226. And there's a few things you're going to need to know to write this. One of the things you're definitely going to need to know is what its atomic number is. Here's radium here, number 88. All elements 84 and up are radioactive, so you want to look starting there probably. So it's atomic number 88. Another thing you're going to want to look up is what its decay mode is, which we'll get from table N. And here is radium-226 right here, and it undergoes alpha decay. I'm going to make a note of that right here while I then look up what alpha decay is in table O. Here it is. I have the option of doing a 4/2 He, because essentially that's a helium nucleus, or I can actually use the alpha symbol. So I'm going to put this as one of my products, 4/2, and I'm going to use alpha. And then my other product has to have a mass and charge that'll make it so that the total mass and charge equals the same as we had on the reactant side. So this must have a mass of 222, and its total charge is 86. So now we just need to look up element number 86, which we're going to find right here as radon. Next question. If 1/32nd of a radioactive sample remains, how many half-lives does this represent? Well, we start with a whole. After one half-life, we have a half. After two half-lives, we have a quarter. After three, we have an eighth. After four, we have a 16th. All I'm doing is doubling my denominator. So after 5, I have 1/32. So the answer is 5 half-lives. Number 8, what's the initial mass of a 3.125 gram sample of a radioisotope given a total elapsed time of 36 hours and a half-life is 6.12 hours? Don't let it overwhelm you. What we need to find out is if that's at the end, if that 3.125 is at the end of some fractional amount, we need to know how many times it's split in half. So if our total elapsed time is 36 hours and the half-life is 6.12, we're going to divide that. So we're going to take 36 hours and we're going to divide by 6.12 in order to find out how many half-lives have elapsed. Now this number doesn't work out to be perfect, and I kind of did that on purpose just in case that ever happens to you. And for this course, all we're going to do is going to round to the nearest numbers. So we had 6 half-lives elapse. So that means at the end of 6 half-lives, we had a total of 3.125 grams. So that means at the end of 5 half-lives, we had twice that, or 6.25 grams. And then we can keep doubling that until we get to prior to the first half-life. So 25 grams, that's after 3 half-lives. 50 must have been after 2. 100 was after 1, so we must have started with 200 grams. That's a 0. And that's our answer. It looks scary, but if you think of it more concrete, like in the box method that I've been using, I think it'll make it a lot easier for you. Next question, what mass of a 60-gram sample, 60-gram sample of potassium-42 will be remaining after 62 hours? So this one, they gave us our initial mass, they told us what isotope we had, and then they gave us our elapsed time. So before we can figure out how many half-lives elapsed, we need to figure out what the half-life of potassium-42 is. Potassium, while it might be tempting to think of it as a P, is actually a K. And its half-life is 12.36 hours. So again, I'm going to take my elapsed time, 62, and I'm going to divide by 12.36. This time we get a number very close to 5. It's 5.01, but again, we will round that to the nearest whole number. So we have 5 half-lives elapsing, so we're going to start with 60 grams. After 1 half-life, we'll have 30. After 2, we'll have 15. After 3, we're going to have 7.5. After 4, we're going to have 3.75. And after 5, we're going to have 1.875 grams. All I did was take that in half after each half-life. Next one. What's the advantage of producing energy by nuclear fission compared to nuclear fusion? We talked about how nuclear fusion, the only waste products are helium and a whole lot of energy, which is awesome because that would be not really waste. Helium's not going to hurt anybody or anything. But the problem is, in order to get the temperatures we need in order to do nuclear fusion, we have to set off a nuclear bomb. and that's not okay. So there's a lot of waste involved there, a lot of destruction. So nuclear fission is the method by which we produce energy in a nuclear power plant, which is very controlled. So we're going to say that we can control nuclear fission. If someone could figure out how to control fusion at a much more reasonable temperature, that would definitely be a better way to do it. A typical fission reactor uses uranium-235, which is really hard to isolate from the other isotopes that are relatively rare on Earth anyhow. A breeder reactor, however, can use uranium-238 and also plutonium-239. While those are rare as well, they're not as rare as uranium-235. So we're going to say it can use uranium-238 or plutonium-239, which a typical fission reactor can't do. Next question, will potassium-39 undergo natural or artificial transmutation? Natural transmutation occurs for all elements number 84 and higher. It also happens with some isotopes of other elements, and most of those are listed in Table N. So since we've already eliminated the fact that potassium doesn't have a high enough atomic number, we're going to check Table N to see if potassium-39 is an option. I see potassium-37 and potassium-42. With the information we have right now, we're going to say that it could not be natural, it would have to be artificial. We're going to say it's artificial because it's not a radioisotope. Next question, can a positron be accelerated to produce an artificial transmutation? An artificial transmutation happens when you bombard a nucleus with a particle. In order to accelerate that particle, it needs to have a charge. So we're going to look in Table O. In Table O, you will find the masses of all the particles as well as their charge. That's the lower number. And for a positron, which is down here, it does have a charge. The reason why it has to have a charge is because we actually use electromagnetic fields in order to accelerate the particle. Since it does have a charge, then yes, it can be accelerated. Number 14, what fraction of cesium-137 will remain after 181.4 years? In order to figure this one out, we need to know what the half-life of cesium-137 is so we can figure out how many half-lives elapsed. Here's cesium-137, it's 30.2 years. So we take our 181.4, or our elapsed time, and divide it by that half-life, which we said is 30.2 years. This one works out to be even closer to a whole number. It's 6.00066, so we're going to say 6 half-lives. So this time, since they're just looking for the fraction, we're going to start with a whole, and after 1 half-life, we're going to have a half. 2 is a quarter. 3 is an eighth. 4 is a 16th. 5 is a 32nd. 32nd. And then after the 6th, we would have 1 64th. Next question, are isotopes of astatine radioactive? So we could look in Table N and see if we find astatine. And these are alphabetical by the symbol, and I don't see astatine here, but it might be one of our elements 84 or higher. So let's look in our periodic table. Here's our periodic table now, and you may need to look in table S if you don't have all the elements memorized, but this is astatine right here, and it's number 85. Starting with element number 84, they're all radioactive. So we're going to go ahead and say yes, and to explain that, we're going to say it is greater than 84. What is the advantage of producing energy by nuclear fission? There were quite a few we went over in the notes. I'm going to use the one that first comes to mind, and that's a huge amount of energy per gram. That's supposed to be a per. Which radioactive isotope would be used as a tracer to locate brain tumors? And that's TC99. And we're not explaining those ones, so that's okay. Which radioisotope could be used to detect thyroid disorders? It can also be used to treat it. And that is iodine 131. Which radioisotope is used to kill insects and meat? That could be Cobalt 60 or Radium 226. You don't need to give both. I'm going to write down both so that you have them both to study from. And then the last one, which radioisotope is used as a tracer to analyze organic reactions during photosynthesis? Now, we only went over one of these in the notes, but you could have oxygen 18 as well as carbon 14. Pretty much anything organic, you really could use carbon 14 to trace it, but probably scientists would use oxygen 18. All right, that's it.